In Core Pure 2, Chapter 2, you looked at the Maclaurin series expansions. What we're going to do for FP1 is investigate Taylor series. We're going to see a more general version of the same idea. So we're going to start with a quick recap of what Maclaurin series does for us, and we're going to begin with an example with sin x. We start by assuming sin x can be written as some infinite polynomial. And then if we set x equal to 0, we can at least work out the value of the constant at the beginning. And it turns out that constant is going to be 0. Sine of 0 has to equal a0, because when we substitute 0 into all of the other terms of this infinite polynomial, we end up with zeros. But then we do something a little bit sneaky. We look back at that first line we wrote, sine x equals a0, etc., and we differentiate both sides. So a0 will now disappear because it's a constant. a1x will differentiate to a1. a2x squared becomes 2a2x, and so on. Sin x, we already know, differentiates to cos x. So we get this. Now, our polynomial is a different polynomial. It's still infinite, but there's a pattern to it now. We can see that the power of x has come down in front for every single term. And if we sub in 0 one more time, we'll find the value of a1, the coefficient of x from the original expansion. But there's nothing stopping us from doing it again. And in fact, provided the function we're dealing with is infinitely differentiable, in other words, we can differentiate it over and over again and evaluate the result. If that's a sensible value, then we can find the coefficients for this expansion. When we differentiate the next time, we can determine that a2 has to be 0. When we do it again, we get a3 is minus 1 over 3 factorial. If you've forgotten where the factorials come from, then look more carefully, maybe pause and have a think about why the terms end up being factorial terms in front of these coefficients. Now, if we carry on for long enough, you'll find that all the even terms, a4, a6, and so on, disappear, and the odd terms end up being alternating signs and reciprocals of factorials. We end up with this beautiful little creature. Sin x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. And that pattern continues forever. You can do a similar thing for many other different functions. And in fact, a lot of them, including this one, are provided for you in the formula book. So you don't necessarily have to memorize them, even if you end up wanting to use them as part of a question. Now, it's worth perhaps for some of you going back and seeing if you can prove the more general Maclaurin series expansion that's provided for you in the formula book. Instead of going through this process that we've just done with sin x, go through it with f of x, and then in place of cos and minus sine and minus cos, you'll have f dashed of x, f double dashed of x, and so on. That should help you to see how this general pattern, including the factorials, comes through with any function you deal with. Now, there's a little bit of a proviso, an asterisk on this infinite series, because if we're going to say something like sin x is equal to some infinite polynomial, well, that doesn't make a whole lot of sense for certain values. For instance, if we have x equals 15, then x cubed over 3 factorial might be quite a lot larger than just x. And in fact, if you've got ever increasing powers of x, how can we be sure that the infinite series even converges? And in some cases, we find there is a limit to the convergence. With sin x, turns out if you go far enough, you can get convergence. In other words, the infinite series will give you a sensible value. But depending on the function, there might be a limited range within which you can go and still get sensible answers. So the question here becomes something to do with limits. We need to know what the value is for the right-hand side, and if that limit exists, then that's what we would think of as being sin x. And that on its own is actually quite useful. You can do a lot with it, even without trying to evaluate the right-hand side. We can substitute things in. We can differentiate it and see what happens to that. There's a variety of interesting things you can do if you think of that infinite series as being somehow the DNA of the function. But what if we just want to find values for sine x? Well, in that case, we could take advantage of the fact that just picking out the first few terms of this doesn't give us the same thing as sine x, but it does give us a good approximation to sine x, provided we're careful with the range of values we might substitute in. The simplest of these you might recognize as being the small angle approximation that was provided for you in the formula book for A-level maths. Sine x is roughly the same as x whenever x is small enough. In other words, whenever x is close to 0. And you can see that if x is a very, very small number, the expansion on the right-hand side is basically going to be dominated by the very first term, x. Because x cubed over 3 factorial is going to be very small if x is very small. And x to the 5 over 5 factorial is going to be smaller still. We can get a better approximation by including more terms. So, for instance, if we start out with the simplest one, 0, it's not particularly good, but x or an x cubed type graph or an x to the 5 type graph will give better and better approximations for a sine wave. So the basic small angle approximation that you've seen, if you wanted a more sophisticated one, you could move up to the cubic version. And if you wanted one that was going to be accurate for an even wider range of terms, then you could move on and use 3 terms. There's nothing stopping you from using as many terms as you like. So this one has, I think, about 20 crossing points. That's not quite the same as the order of the polynomial because the roots don't perfectly correspond to the crossing points here. But you can see that this curve is going to resemble y equals sine x for most of that range between, more or less, between minus 9 pi and 9 pi. So it does a remarkably good job. But it will be a rather computationally intensive way of approximating the value of sine 20 pi or even sine of 100 pi. If you ask your calculator a question like that, it doesn't seem to have too much of a problem with it. It's obviously not calculating a wider and wider range until eventually it gets to 100 pi. It's got some clever trickery going on. So we know that if we've got enough terms, we can get a decent approximation. For something like sine, we just go far enough, we'll eventually find our value. But that's not necessarily good enough for us, and that's why we do Taylor series. So far, this graph is a cubic, but the precise nature of that cubic changes depending on where the dotted line goes. Now we're looking at some more complicated polynomials. They are all still doing a similar thing. Can you figure out what it is these curves are attempting to do? Where do you think they come from? How were they generated? And what's the relevance of that dotted line? Well, in case you haven't guessed yet, these are increasingly good approximations for the sine wave. The sine function there in green is being approximated by these various polynomials that you can see, but they are different depending on where the dotted line goes. These adapt their accuracy and their efficiency of approximation based on the point at which we choose to evaluate them. So it's obviously possible to do the equivalent of a Maclaurin series expansion, but to have it centered somewhere other than the origin. And yet it feels like it shouldn't be, because the whole process we went through involved substituting in 0 and having an infinite list of terms just disappear because it was 0 squared and 0 cubed and so on. So we're going to need a bit of sleight of hand when we try to do this for ourselves. We know that Maclaurin series gives a good approximation for the value of a function when we're close to the origin, close to x equals 0, but we can apply some clever adaptations and trick it into giving us an approximation which is accurate close to whatever input value we particularly care about. Let's see what that's going to look like. See if we can find a Taylor series expansion for the function f of x when x equals a. so any value that we are interested in. Let's start by defining a new function, which is going to be a translated version of that function. I'm going to shift it to the left by a units so that the new function is somewhere different to the old function. Then we're going to find the series expansion of the new function when x equals 0. And this is quite a clever trick. You see, we care about f of x, but we're going to use g of x to get our series expansion. And we know that because of the process we can follow with Maclaurin series, we can generate an expansion that works for g of x. In fact, we've already got one. We know Maclaurin series, we can just quote the formula directly, g of 0 plus g dash of 0 x, etc., etc. Now, once we've got this, we need some way to rewrite it so that it involves f of x rather than g of x. Well, luckily, g of x can directly be swapped out for f of x plus a, so that's nice and simple. And also notice this, that g naught is the same as f of a, because g of x is f of x add a. But it gets better. We've got chain rule comes to our aid here. If we're interested in finding the derivative g dashed of x, doesn't matter what the function f is, g is just a horizontally translated version of f. So the derivative will be a horizontally translated version of the derivative of f. You could think of it as chain rule if you prefer. If you want to differentiate f of x plus a, then you get f dashed of x plus a multiplied by the derivative of x plus a. And because we've not done any stretching or squashing, the derivative of x plus a is just the derivative of x, so it's just 1. That means that g dashed of 0 is the same as f dashed of 0 plus a. And g double dashed of 0 will be f double dashed of a, and so on and so forth. And we generate a very similar looking, but crucially different formula. This is our formula. G of x becomes f of x plus a, g of 0 becomes f of a, g dashed of 0 becomes f dashed of a, and so on. Now this means, provided we can evaluate the derivative of our function and substitute in the value we care about at all the different places, we can generate for ourselves a custom infinite series that gives us the value not of f of x, but of f of x plus a. Now, that may not seem to be quite what we were looking for. In fact, I've said I want to find the Taylor series expansion for f of x. But bear in mind, this will give us something useful. The other thing to notice here is this formula is not provided in the formula book. It's quite often used, or it's requested, or that you will need to make use of it yourself within a question. So you want to make sure you can reproduce it for yourself by comparing closely to the Maclaurin's series expansion that is provided in the formula book, which I've copied here for you. So look at what's different. They have f of x, we've got f of x plus a. They have f of 0, we have f of a. They've got f dashed of 0, we've got f dashed of a. Apart from that, all the way through, the overall structure is the same. So pay close attention to that, identify what's going to be different, and make sure that you're comfortable adjusting this to find the more general version. This means we've basically got two key steps. We're going to shift the function to the left, and then we're going to find the Maclaurin series expansion at 0, because we know we can find the expansion when x is 0, and this trick allows me to basically cheat and use a different function, find the expansion at 0, but I know that when x is 0 for the translated function, that's equivalent to finding what I wanted anyway, which was f of a. So when x is close to 0, we'll be using our expansion to calculate the value of f of something close to 0 plus a. In other words, a value that's close to f of a. So if you want sine of 100 pi, well, you could just shift the sine wave 100 pi units to the left, and then calculate the value of sine of something close to 0 plus 100 pi. You've got values close to the number you're interested in. But we can do a little bit better still. So although that format is often quite useful and will be used in its own right, if we really want an expansion for f of x, then we just have one last step to do. And it's not a particularly complicated step either, so don't worry. The clever stuff is behind us. This bit is just a bit of substitution. We want to get f of x instead of f of x plus a. Well, we're just going to take the expansion we already have, and we do a substitution. So in place of x, we're going to write x minus a. And then on the left, it'll be f of x minus a plus a, which is just f of x. And all the way through the expansion, our powers of x become powers of x minus a. So the expansion starts to look a little bit weird. And crucially, this sort of expansion is going to be a good approximation, provided the powers of x minus a become small enough, which is another way of saying that x needs to be close to a. Notice it now says f of x. So this is the expansion we're interested in. It gives us f of x, and it gives it in the form of a polynomial that, yes, is written in a slightly weird way, and I suppose if you really wanted to, you could expand out some of those brackets and turn it into a simplified form of a polynomial with powers of x. And sometimes you might do that, depending on the question, but a lot of the time, this format will be just fine as it is. Remember, it's just one quick step away from the other one. So if you can use the formula book to help you remember the first form of the expansion, then you can use quick substitution to convert it into the second form, which gives us this slightly updated version of the intuition behind the Taylor series expansion work. Step 1, shift the original function to the left by a. Of course, if a is a negative number, you can think of this the other way around, but essentially we're shifting the original function. We're finding the Maclaurin series expansion at the origin. And then, if you like, we can bring in step 3, where we shift the whole thing back the other way, including the series expansion. So by shifting left and then shifting back to the right, you're back at your original function. We shifted left, then we performed the Maclaurin series expansion, and then we shifted the series expansion back to the right, meaning instead of being centered at 0, it's now centered at a. And that's, I think, in some ways a little nicer, a little more sensible, feels more intuitive to us, because if you want to approximate a value that's close to f of a, then you just put in a value for x which is close to a. Now I'm going to give you the opportunity to try this for yourselves. Remember, you can make use of these formulae. So start with the very first one, and in place of f you're going to use sine x. In place of a, we're interested in the value pi, so we want to find a series expansion for sine x, which instead of being good when x is a very, very small number, we want one that's good when x is very, very close to pi radians. Have a go at this, and if you manage to make it work, then I want you to have a go at using your expansion to estimate the value of sine 3. 3 is pretty close to pi, so it should give a reasonably good approximation if we use this expansion. I'd encourage you to pause the video at this point and give this problem a try, and when you're ready, we'll work through it together. Okay, here's my first line. F of x plus a is sine of x plus pi. And I could write out explicitly my various derivatives at the beginning. For some of the more complicated functions, that might be helpful, add a bit of structure to things. But in this case, because sine differentiates to cos, which differentiates to minus sine, which differentiates to minus cos, it's simple enough to write them all out at once, like this. Also, because I'm putting in pi, a lot of these will simplify quite nicely. So sine pi, for instance, will cancel out because sine pi is 0. Cos pi, on the other hand, is negative 1. So we're going to end up with minus x plus x cubed over 3 factorial. And this is the first form of the expansion, you might recall. This is the version we have at the top of our list, the two different sorts. And if we wanted to, we could use this. So if we were going to calculate the value of sine 3, we could just say, well, let's make x equal to 3 minus pi. And then when you add pi to that, you get sine of 3. And the usefulness of that is that 3 minus pi is a good value for x to put in, because that's close to 0. But it can get a little confusing. So the alternative is to do the substitution straight away, to replace x with x minus pi. And on the left, that gives you sine of x. and on the right it gives you minus x minus pi instead of minus x, and it gives you x minus pi cubed over 3 factorial instead of x cubed over 3 factorial. And now you can sub in whatever you like. So you can put in 3, we get minus 3 minus x, add 3 minus x cubed over 3 factorial. You can evaluate that, and we get 0.1411, which in fact is accurate to 4 decimal places. So it's a surprisingly good approximation for the value of sine. If you were going to use the original sine expansion, the Maclaurin series expansion that's centered at 0, it gives you something daft like minus 1.5 if you evaluate up to the cubic term. So the version centered at 0, you're going to need to include a lot more terms in order to get a decent approximation for sine 3. The angle is just too big for it to be close enough to 0. But since we've specifically designed our expansion to be accurate when x is close to pi, when we try using it to approximate sine 3, it works really well. Here's a few others you could try. I've had a go at approximating sine of 3.4. That also works pretty well. It's not quite as accurate as sine of 3. And also sine of 22 over 7, 3.142857 recurring. And that one was accurate to one place in a billion or something. You can see that it's not going to work so well if you try sine of 2, although still within 2%, it's not too bad. Sine of 0, on the other hand, things just go a bit crazy. The true value is 0, and yet our approximation is coming out as a number like minus 2 point something. So you can't even calculate the percentage error with something like that, because one number is 0, the other one is something finite. So it doesn't work close to 0, but it does work close to pi. This is what the graph looks like. So in green, we've got y equals sine x. And then you can see this is a cubic, just like we would normally get for the standard Maclaurin series expansion. But instead, we've got something which is most accurate when x is very close to pi. In fact, it's precisely the same if x is exactly equal to pi. And then it gives very good results for any values of x that are close to pi, and it gets increasingly bad as x gets further and further away from pi. We're going to go through one more similar example graphically. So we're going to look at a series expansion for sine x, which is accurate close to x equals 1. We'll start with this. The original curve is in red, f of x equals sine x, and we've got the translated version. We've dragged it to the left, and the link's there if you want to play with this yourself on GeoGebra online. If we pull that function to the left, then we generate a new function. That new function can then have Maclaurin series expansion applied at the origin, and we can generate a series expansion, in other words, an approximation as a polynomial for that curve to however many places we care. In this case, for instance, we've got something that gives what looks like a reasonably good approximation up to maybe minus 1.5 on one side and up to perhaps 2 on the other side. But notice this is an approximation for the new function, the translated version. We shift the function to the left, we find a series expansion for the translated version, and then we shift back again. And now the series expansion is valid for one place to the right of the origin. We pull the function to the left, we find the series expansion at 0, and then we push it back to the right again, including the series expansion, and we end up with something which is accurate for values that are close to x equals 1.